two topics in the course in managerial economics, so that's why we're going to start with that. And decision analysis is normative decision theory. In other words, when we do decision analysis, we're going to try to find out how someone should make decisions, how a decision maker should make decisions if he wants to maximize their utility or scale. So it's not about describing how people make decisions, so how do they act in real life, but it's more about how they should behave given a certain utility context, given a certain set of preferences. And most of the time, these decisions are made under a degree of uncertainty. So, what are some of these decisions under uncertainty? If I'm a manager figuring out how to structure my supply, right? Some decisions we make is which suppliers we would want to select. And very common. So how do we select suppliers? Which kind of suppliers should we select? Well, of course, one important issue here is that whenever we make a decision on supplier A versus supplier B, we don't know exactly how they're going to perform in this particular supply relationship. How many suppliers? So there may be a benefit in choosing a single supplier because that's going to give us a better market position vis-a-vis that supplier. But on the other hand, we may want to have multiple suppliers because we can insure ourselves against the other person, the other supplier, basically going bankrupt or not delivering in the way that he should be. R&D decisions and investment decisions. So as I just mentioned about the 4 exams in the 8 weeks, we all make investment decisions. And in corporate settings, in firm settings, lots of these investments are R&D investments. So the question here is, under or among a large set of possible projects, which projects am I going to choose? Which are the ones that we're going for? Do I go for something that's very risky, or do I go for something that's pretty safe? Do I just carry on what I do or what I did before, or do I go into new businesses, new branches, new types of markets, and so on? So these are all decisions that we have to make under the degree of uncertainty. Hiring and promotion decisions. So at some point you're going to be graduating, and when you graduate, you're going to look for a job. So you're going to send out your CV, and your CV amongst 200 others is going to land on the desk of some HR person. So that HR person is going to look at your CVs, and on there it probably gives you, where it gives information on your degree, on the subjects you studied, on your average marks, on the high school you attended, probably on some work experience that you've gained, and that's pretty much it. Okay. So based on that information, and maybe based on another interview that you have after that, but based on that information, someone's going to have to make a decision whether to hire you or not. And I'm sure you'll agree, I hope you'll agree, that your CV is only an imperfect measure of how well you're going to do in a particular job, right? Even if we just assume that every job is the same for now, right? Even then, it's not entirely clear if, let's say, your mark in managerial economics is a great indicator of how good a manager you're going to be, right? So if you have 95% in managerial economics, does that mean that you're bound to make fantastic decisions for the firm? Okay. If you are good in financial accounting, does that make you a good accountant? Again, maybe there's some correlation, but the correlation is definitely not perfect, right? Personality, and your personality doesn't really feature on your CV. So people write in, I'm hardworking, I'm a team player, I'm a really nice guy, I'm driven, I'm ambitious, right? Many CVs will have those kinds of terms. Doesn't really say much. I can write, I'm driven. What does that mean? So, in that sense, every hiring decision is going to be made under a great deal of uncertainty. You might argue that promotion decisions are a bit more straightforward because at least after a couple of years, I should know exactly how these people perform in their job. Fine. But even if I know how they perform in the job, that doesn't tell me anything about whether I can promote them or not. Right? So there's a thing called the Peter Principle, and the Peter Principle says that people get promoted up to the point of their incompetence. And what does that mean, and how does that work? Well, let's say you're a fantastic junior consultant. Okay, you go work for a consultancy, and you end up being a great junior consultant. Now, as a junior consultant, probably the dimensions of success is how many hours am I willing to put in, and basically, am I going to knuckle down and really implement the solutions that I'm supposed to. Now, if I'm really good at that, I get promoted to consultant. As a consultant, my job now is to develop these solutions and basically to hand them down to junior consultants to implement. Now, does the fact that I'm good at implementing make me necessarily make me a good person at coming up with these solutions? Maybe, but maybe not. So I get assigned a new role, and because I'm good at the old role, right? So as long as I'm good at the existing role, I get promoted, right? So I get promoted from consultant to team leader. Now, as a team leader, I'm supposed to manage the team. Problem is, if I'm great at coming up with solutions, which is what got me into the team leader position in the first place, I may not be a good person at managing people. Right? You see that a lot, actually, in investment banking, when all of a sudden people are in charge of an investment banking or an entire investment banking team. And the ones that are particularly good are basically often not the ones that are people persons, right? So they're often the ones that are really focused on delivering the numbers. So basically, you get promoted as long as you do a good job, and once you don't do a good job anymore, because you're not suited for the job, you don't get promoted anymore. So that's the Peter Principle, right? So as long as you do well, you go one step further up. If you don't do well, you stick to where you are. So the things that you don't do well are the ones that you get promoted. So even promotion decisions are made under a significant degree of uncertainty in firms. We can think of two dimensions or two big categories. We can make decisions where one person, myself, let's say, is the only rational decision maker. So there's only one rational decision maker, and everything else around me is basically a set of random events. So when I wake up in the morning, I'm going to have to decide if I take an umbrella with me or I don't. So I'm going to make this decision based on my guess on how likely it is that it's going to rain or not. Now, rain or the weather isn't a rational player that plays against you, right? So the weather doesn't feel better if it manages to soak me, right? But the weather basically is, from my perspective, is a random event, which means that there's a probability that it's going to rain, there's a probability that it's going to be overcast, and there's a probability that it's going to be sunny. This is the set of problems when we have when we apply decision analysis. When we have two or more rational decision makers that take also into account that other players will play in a rational way, and other players will affect my payoffs, we're looking at game theory. So it then becomes a strategic decision, right? So my decision is now dependent on my guess on what you're going to do, and vice versa. Okay. I should almost be embarrassed to tell you this, but I'm not, because in all the many exams that I've seen, in the many scripts that I've seen, one pattern I think is clear. Many candidates get the basics wrong, and the basics are typically the easiest ones, right? So you want to. I have perfect understanding. I perfectly understand if some of the questions just are very difficult, especially in a high-pressure exam type setting, and so you don't get them completely right. There is really no excuse for not getting the basics right. Okay, and so therefore, and basically, if you don't get the basics right, two things are going to happen. First of all, your follow-on solutions are going to be wrong. And second of all, you're going to lose points, right? And when you're at just below the pass rate, then yeah, you want those 3 points that you would have gotten for setting up the problem correctly, right? Or when you're at 68%, yes, the basics, getting the basics right to get these extra 3 points or extra 2 points is an important bit, right? So do make sure you get the basic features of the course correct. And so one of the things that that I'm always struck by is the fact that people sometimes do have problems setting up a decision tree in the right way. So that's why I'm going to go through the basics. If you have a decision node, right? A decision node is when a decision maker makes a conscious decision. When I decide if I want to take an umbrella or not, that's a conscious decision. When I decide to continue pursuing an activity, that's not a random decision, that's a conscious decision. So once I have that, if I have that, I will draw this as a square. Okay? When I draw this as a square, it always means that this is a conscious decision bias. If I have a probability node, which means that it could go one way, it could go the other way, but this is not a deliberate decision, then I'm going to draw a circle. Okay? Whenever uncertainty is resolved, I draw it as a circle. And so, for example, if the weather could be sunny, overcast, or raining, then that's a random decision. And so I have to draw a circle, and I have to draw 3 branches going from that. So branches coming from a probability node are the possible different outcomes of this uncertain situation. It could be sunny, overcast, or raining. So that's 3 options, 3 branches going from the probability. I could take an umbrella or not, so I have 2 decisions. I could take it or I couldn't take it. So I have 2 branches leading from the decision node. The payoffs are going to be written at the end of the final branches. And the probabilities are written at the branches leading from the probability. And again, a trivial but important detail, the probabilities have to add up. Okay? Because one of the things is going to. If they don't add up to 1, then you are doing something wrong. And something needs to be correct. And so I always feel that the best way to do these things is to actually practice them and to use real So imagine you are the manager of an IT manufacturer and your choice is to advertise your product on all channels. of advertising will be £100,000, and sales can be either high or low. If you do advertise, then sales are going to be high with a 90% probability. If you don't, you're only high with a 60% probability. Of course, that means that sales are low with the low probability of 1 minus 0.916. If sales are high, you will earn £300,000, excluding advertising costs. And if they're low, your loss is going to be 100,000. And that's really the information. That's all the information that we need to draw a decision. Which is going to look like this. So the first decision is if the manager wants to advertise or not. If he doesn't advertise, he's going to make high sales with 60% probability, and in that case, he's going to just make 300,000. Or he makes low sales, which makes him lose 100,000, but the probability of that is 42%. If he does advertise, then there's a 90% chance that he makes high sales, and high sales means 300,000 minus 100,000 because he spent money on advertising, right? So that leaves you 200,000. And if you make low sales despite advertising, you're actually losing 200,000. But the probability of that happening is only 10%. Good, so what do we do in such a situation? In such a situation, we apply, or we try to maximize expected profits. And if we maximize, or to maximize expected profits, we basically have to look at the expected profit in both of these cases. If we don't advertise, there's a 0.6 probability of high sales, which means 0.6 times 300,000. That's 180. Minus 0.4 times 100,000, because we're losing 100,000 with 40% probability, so that's minus 40. Meaning that if you don't advertise, your expected profits are going to be £140,000. Advertising, on the other hand, gives you high sales with 90%, and so 0.9 times 200 is 180 again. But 0.1 times minus 200 is minus 20 only, so that means that advertising gives you an expected profit of 160,000. So as a consequence, when choosing between advertising and not advertising, your expected profit is going to be higher from advertising than not, so you're going to choose to advertise. One important point, and that just came to my mind, often candidates that also bold or double mark the high sales strategy. So basically they end up at this 200,000. That's not right? Because this is not the decision of the decision maker, right? I do not choose to get this. I choose to advertise or not to advertise. So I cannot decide that there's going to be high sales. So that means that I can only ever double mark, I can only ever put the advertising bold if I want to indicate that this is what the manager is doing. So this also reminds us of some properties of this industry, something that are, I guess, conditions, ways of checking whether we've done it right or not. There are no loops, so we can't go back to the same situation as before. For example, if I decide not to take an umbrella, I go down and I leave the house. I find out that it's drizzling a little bit, and then I go back up to get my umbrella. This is not the same decision because I'm making this decision with a different information set. some percentage chance that I'm going to that is going to rain. Now I go out and I see that it's drizzling. I've actually gained more information. So I've acquired more information. There are no loops in any decision tree here. We start out with one initial node, and that node is either the resolution of uncertainty or a decision on my part. There is at most one branch between any two nodes, and the decision tree. So these are all kind of just features of the decision trees that we'll have to take into account. And at any decision node, then the decision maker will have to have all information on preceding events, in particular on the kind of uncertainty that's being resolved. Let's look at a slightly more complex, slightly more involved example, oil drilling, which is a two-stage decision. So you have to decide whether you want to drill or not. And if you drill, then you have to decide how deeply you want to drill. So to drill the first layer, it's going to cost you 160,000 pounds. And drilling the first 3,000 feet gives you a 40% chance of strike. If you do strike oil, then profit is going to be 60,000. If you don't, you can drill in a second layer, and that second layer is going to cost you another 90,000. And the chance of oil striking oil in this second layer is 20%. If you do strike oil in that second layer, you're going to make 400,000. So if we wanted to maximize profit, what are we going to do? Well, here's your decision tree. First decision is, does the manager want to drill or not? If he doesn't drill, he doesn't incur any costs, but he doesn't get any profits either. So that's the thing here. Then he has to decide if he wants to drill, or if he's decided that he wants to drill, then there's a resolution of some random event. And that random event is, do I strike oil or do I not? If I strike oil, again, it's over. So the decision structure is over. This happens with a 40% likelihood, and I'm going to make profits of 600,000. If I don't strike oil, then I'm facing the second decision. My second decision is, do I want to continue drilling or do I stop it here? If I stop it here, I've wasted the first 160,000 because I didn't strike oil, and I'm not doing anything about it in the second layer. So I lose on it. If I continue drilling, then again some uncertainty gets resolved. And that uncertainty is going to tell me if I'm going to strike oil or not in the second layer. Not striking oil is an 80% probability event, and I will have lost 160 from the first layer and another 90 from the second layer. Striking oil happens with 20% likelihood, and that means 400,000 days. So to make a decision here, I want to find the expected monetary value. I want to basically maximize the expected profit. So to maximize the effective profit, the one complication that we're facing here is the expected profits that we have here. So the expected profits that we get here are basically the result of the conscious decision to not continue drilling or to continue drilling, and then of the resolution of some uncertainty. So if we wanted to put an expected value here, it would be very easy. So what do? Well, we look at this point. We look at this at this node here. We know what the expected profits here are. That's minus 460. And now let's have a look at what the expected profits on the other side. If we continue drilling, there's an 80% of chance of losing 450. So it's 0.8 minus times minus 250. So that's minus 200. plus 20%, I'm going to strike oil and get 400, which means 0.2 times 480, so it's minus 200 plus 80, so my expected losses from continuing to drill are 120. Now if we compare 160 to 120, it's of course preferable to continue drilling because that makes me lose less than lose less than if I just stop drilling. So this minus 120 is then what we can use as the expected profit at this point. Meaning that if I drill, there's two things that can happen. I am lucky, and with 40% I'm going to strike 200. 0.4 times 600 is 240. And with 0.6, I'm going to be in the state to continue drilling, and in that case, I'm going to expect minus 120, minus 120 in the second state. So I get 0.6 times minus 120, that's minus 72. So we've got 240 minus 72, so my expected profits from drilling are 168. 140 minus 72. So 168, and I compare the 168 to not drilling and getting 0. So of course I'm going to drill. And here again, what are the things that I can decide? I can decide to drill or not. So I can double mark this, and I can decide to drill further or not. So I can also double mark this. These are not decisions of mine, right? This and this. These are random events. Now, previously we've looked at, as I said, we've looked at maximizing expected profits. And for many situations, this is right. Often when we think of firms, we always when I taught on Saturday, this was also the same room, and there was drilling going on literally outside this door. So this is okay. This is still okay, but if this goes on, I'm going to speak to someone. But yeah, let's see. Okay. Anyway, this looking at expected profits was is often good when you look at decision making by firms because their business is to maximize profits. Now, when we're looking at individual decision making, it's often not so easy. And here, for example, we have a very simple situation. And that simple situation is as follows. I can choose to get 99 pounds for sure, or I could get a lottery ticket, and that lottery ticket is going to pay out 200 pounds with 50% chance, and it's going to pay out nothing with 50% chance. Now, knowing you, or not knowing you, but knowing kind of humans in general, about 2/3 of you would choose to go up rather than down. Okay, so 2/3 of you prefer getting 99 pounds for sure over getting 100 pounds in expectation. And so if you were rational profit maximizers, this would not be a smart idea. Right? Because as profit maximizers, you want whatever gives you the highest expected profit. And the higher expected profits here are 100, assuming you take the lottery ticket. If the decision maker decides to take the 99, i.e. 2/3 of you are risk averse. And we can think about risk aversion in several ways. We will do that for the next half hour. But risk aversion basically means that if I give you two options, those would be the same in terms of expected profits, but one would be less uncertain than the other one. You would take the less uncertain one. And here, 2/3 of you are actually happy to take something that has a lower payoff, but more certain. Right? So here, getting 99 pounds for sure is better than getting 100 pounds in expectation. So think of risk aversion. You can say that a decision maker is risk averse. He prefers a certain outcome of X over a risky project with a mean expected monetary value of X. The decision maker is risk loving if he prefers a risky project with this expected monetary value of X with a certain outcome of X. So, in other words, if you were happy to buy a lottery ticket with an expected payoff of £5, and you'd be willing to pay £5 for it, then that would mark you out as a risk lover. And you are risk neutral if you are indifferent between a certain payoff and an uncertain outcome with the same expected monetary value. And in some ways, this is the easiest case, the risk neutrality case, because there, what you do is you simply maximize expected profit. Okay? You don't care about the degree of uncertainty, you just maximize expected profit. Now, a closely related concept to risk aversion is the concept of risk aversion, of certainty equivalent. The certainty equivalent is the amount of money that makes the decision maker indifferent between receiving this amount for sure and the risk equivalent. So let's sink in for a bit. So here you're facing that situation where you can either go up and get X pounds, or you can go down and get 100 pounds of expectation because you're getting a random draw between 0 and 200 with equal probability. So the certainty equivalent here is exactly the amount of money that I need to give you for sure, so that you're indifferent between the lottery and the certain amount. So that means that if you are, if you are risk averse, for example, if you're risk averse, you might be willing to take an amount of 80 pounds, and you're still indifferent between the lottery that pays out 100 pounds or 80 pounds for sure. So that means that the certainty equivalent of the lottery with 100 pounds expected value is 80 pounds. Okay. So that's the idea of the certainty equivalent. How much do I have to pay you for sure so that you are indifferent between an uncertain outcome and between an uncertain lottery and a certain thing. And for risk-averse decision makers, the certainty equivalent is always going to be lower than the expected monetary value of the loss. So, even more closely, or still closely related to the concept of risk premium, to the concept of certainty equivalent, is the concept of the risk. Risk premium is simply the cost of risk. And we derive that by taking the expected monetary value and subtracting the certainty equivalent. And the idea here is that a risky project is costly to the decision maker because it reduces her expected utility compared to the certain prospect of receiving X. So you've got a lottery. And I'm going to tell you, well, 100 pounds is 100 pounds. So 100 pounds in expectation should be the same, be worth the same to you as 100 pounds for sure. Right? But that's not the case if you're risk averse. If you're risk averse, 100 pounds in expectation is actually worse. So once that's the case, I'm going to ask you, well, how much are you willing to give up of the expected value so that you're willing to, so that you're indifferent between the certain outcome and the expected monetary value. And the difference between the certainty equivalent and the expected monetary value is the risk premium. So that is how much you would be willing to pay to avoid risk. Okay. So that means that if the certainty equivalent is less than the expected monetary value, you are risk averse. And of course, the larger the risk premium, the larger the difference between EMV and certainty equivalent, the more risk averse you are. So in other words, if I were super risk averse, I would say, well, rather than facing the danger of losing zero, of getting nothing, I'm happy just with 20 pounds, right? So give me 20 pounds, and I'm willing to give up my lottery ticket that possibly will pay out 200. In that case, that would make me extremely risk averse. If I'm almost risk neutral, then it's going to mean, well, you're going to have to pay me 95 pounds, so that I'm indifferent between the lottery of 100 and the certainty equivalent of 95. So my risk premium is very small. Which means, of course, that's also how insurance companies work. So their point, or their idea is that they make people pay the risk premium in return for taking over their risk. Right? So getting car insurance means here that the variance of your outcome is not the crash of the car, not the lose the entire car. So the variance of outcome is smaller, but you're going to have to pay for this. So you're going to have to pay some premium to the If the certainty equivalent is equal to the expected monetary value, then you are risk neutral, and every decision maker who's risk neutral is going to use the expected monetary value criteria. In other words, he's going to maximize. And if the certainty equivalent is larger than the expected monetary value, you're a risk lover. So that means here that you're actually going to have to pay me more than the expected value of the lottery, so I'm willing to give up my lottery ticket. And if you and we've been talking about lottery tickets, but let's now literally think of a lottery ticket. If you buy a lottery ticket, the expected monetary value of that lottery ticket is what? Maybe $2. So let's think. I mean, there's a chance of winning $20 million, okay? And the chance of winning $20 million is 1 in 100 million. Okay? What does that mean? The expected value of the main prize is 1/5 of a dollar. Okay? 20 million divided by 100. In the end, you can get some intermediate gains and prizes and so on. But let's just say that the expected value of a lottery ticket is $2. Of course, with a huge upside, right? If you just strike the jackpot, you're going to be 20 million. You're going to be 20 million richer. Now, most people are willing to pay much more than $2 for the lottery ticket, right? If you buy a lottery ticket, then it's not $2; it's maybe $5. What does that mean? It means that the certainty equivalent, you're actually willing to give up $5 in return for a lottery ticket with an expected value of $2. So that means that you are not even indifferent, you prefer giving up $5 in return for this huge potential upside. Okay. That marks you out as a risk lover. Okay. If the certainty equivalent is larger than the EMD, the expected monetary value, then you're a risk lover. Which of course makes it bizarre that people who are insured buy lottery tickets. People who are insured are ones with a certainty equivalent less than the expected monetary value. People who buy lottery tickets are people with a certainty equivalent that's higher than the expected monetary value. Okay, so in principle, these two types of behavior are inconsistent with each other. Risk premium, what's obvious here is that we cannot use the expected monetary value criterion just like that. We cannot use that forever, and we cannot use it for everyone. So one easier, or one way to solve this is to think about expected utility rather than expected profits. And the aim of that is that we want to allow for the fact that people have different risk attitudes. Right? So a lottery ticket with 200 or 0 may not mean the same to all of us. Okay? We have different risk attitudes. So it may not be, I may be happy with 80 pounds in return for the lottery ticket, others may be wanting 95 pounds, and others would be so risk averse that they prefer 50 pounds over the lottery ticket with an expected value of 100. So what we do is we need to compare, or we need to transform monetary values to utility values. Okay? And if we have the utility function, then it's actually very easy. Right? If we have the utility function, and here is an example, if we know that 0 payoff gives us 0 utility, 200 pounds gives us 100 in utility, and 99 pounds gives us 80 in utility, then we can just apply, very simply, we can apply the expected utility criterion. So the expected utility of going up is 90, expected utility of going down is 50% times 0, plus 50% times 100 is 50. So the decision maker will choose up rather than down. Of course, the issue is that often we don't know what the utilities exactly are. Okay, so we have to make a trade. We have to make things in a smart way. And, so I'm going to spend some time on this. Suppose we have a problem with 5 different payoffs. You lose 100 pounds, you win 500 pounds, or you win 0, 100, or 50 pounds. So if we wanted to find out what the utility of 100 pounds is, we would set the utility of the highest monetary payoff to 100, and we would set the utility of the lowest monetary payoff to 0. Meaning that if you lose 100 pounds, that's going to give you a utility of 0. And if you win 500 pounds, your utility is going to be 100. If we then wanted to find the utility of 100, we ask the decision maker, for which probability is the difference between going up and down in the following case. Now let me if we make a decision to go up, we get 100 pounds, right? That's the payoff for which we want to find out the utility. If we go down, there's going to be one of two things happening. Either we lose 100 with probability P, or we win 500 with probability 100. So the useful thing is that we know what the utilities are for this, and we know what the utility is for this, right? For 500 pounds, it's 100. For minus 100, it's 0. What we know is that the utility for 100 pounds is somewhere between 0 and 100. Often, right? So it can't be worse than losing 100, but it can't be better than winning 500. So it has to be somewhere in between. Now, if that person tells us that, to be indifferent between going up and down, to be indifferent between getting 100 pounds or playing the lottery would have to have a success probability of 50%. So this would be 0.5 0.5 to 3.5. Here's the trick. Here's the trick. We need, so one thing is that we ask the decision maker for the point of his indifference. Okay. What does indifference mean? Indifference means that he gets the same expected utility from going up and going down. Okay. So indifference is, I mean, you all know kind of intuitively what indifference means, but in a setting, in a decision analysis setting, it's important because indifference basically allows you to set the utility equal. So it allows you to set the utility equal, which means that if I just ask this decision maker for his probability that makes him indifferent between this and that, I basically ask him for the point at which these two utilities are the same. So that means that we can usually write the utility of 100 pounds. Right? The utility from going up is equal to P times U of minus 100 plus 1 minus P times U of 500. In other words, all we're doing here is we're saying this decision maker is indifferent between going up and down. So that's the utility of going up. That's the utility of going down. Now we know that U of minus 100, utility of minus 100 is 0. The utility of 500 is 1 minus P. So given that our decision maker answers that it's going to be 1/2, what makes him indifferent is 1/2. What we can say here is that the utility of 100 pounds is going to be 1 minus P, that's 0.5 times 100. That's the utility of 100 pounds. So in other words, the utility of getting 100 pounds is less than 100, it's more than 0, it's actually 2. So the utility from 100 pounds is 2. So what's important here on this slide is this concept of indifference. Okay? Whenever we see indifference, whenever we see I don't care between either one option or the other, it means that I can take the two utilities and set it equal. Actually, this is going to be important when we think about one of the mock examples. Right? One of the mock examples is, well, show that you would not pick one over the other and at the same time pick another, make another choice in another decision tree. If you pick one over the other, that's nothing else but saying you get a higher utility from the option that you choose than from the option that you don't. And that's going to be that's going to be useful later on. Okay. Now, thinking about all these utilities, of course, what we would like to do is eventually find the utility function. So you will want to figure out what the utility function is. Basically, make statements about what choices they're likely to make. And so, we're going to go through 3 utility functions, or statements of 3 utility functions. Risk neutral, risk averse, and risk loving. So the utility function of a risk neutral decision maker is 0. What does that mean? It means that the expected utility of a lottery that pays out 200 pounds with a probability P and 0 with a probability of 1 minus P is equal to the utility of 200 times P. Right? Because we know if we lose, we get 0 utility, and that's going to be 100 times. What does that mean? Well, again, we've set utilities between 0 and 100, because we make no profit, we get no payout, we get a utility of 0. If we get 200 pounds, we get a utility of 1. Okay. So the expected utility of this lottery is going to be 100 times. So, if we took the expected monetary value, right? If I gave you the expected monetary value for sure, that would be P times 200 pounds as well. So in this case, the expected monetary value is equal to the certainty equivalent, right? As we saw before. But what this means is that it doesn't matter if I get a lottery ticket with 0 with a certain probability and 200 with a probability of C, or if you get the amount of money for sure, the expected amount of money for sure. So this is why the utility function of this risk neutral decision maker is linear in line. What this also means is that an extra 10 pounds, if we start at 0, is going to be worth the same extra utility to me as an extra 10 pounds starting from 190. Right? So if I give you 10 pounds, it's always going to be worth the same to you in utility terms, regardless of what you already have, regardless of your dollar. Good. So that was the easy bit. Now let's have a look at the utility function of the risk of first decision making. And before we can look at the utility function, let's look at the graph and see what the two lines are that we have on. First, we have this diagonal line. What is this diagonal line? The diagonal line is the line that gives us the expected utility of the lottery ticket, which is 0 and 2. In other words, if I gave you a lottery ticket with an expected monetary value down here, which means that you get 0 with a certain probability and you get 200 with a certain probability, the expected utility is going to be a combination of 0 utility plus utility of 100, utility of 200 pounds. So that's going to put you somewhere here. So that is the combination. So that diagonal line is a combination of 0 utility, utility of 200 pounds with a certain probability. And so of course, if the probability of gaining 200 pounds is very large, then your expected utility is going to be very large, right? So that's why it's an increasing diagonal. Good. So the utility function, and you remember that when you've been given utility function. Utility function is basically a function of the amount of money that we have. Right? So that means that the utility function tells me if I get a certain amount of money, how much is that worth to me in utility terms. Right? And it always refers to certain amounts of money. Right? So the utility function tells me if I give you 100 pounds, what's your utility? If I give you 0 pounds, what's your utility? If I give you 150 pounds, what's the utility you get? And this is this curved line. So the curved line tells me something. It tells me if I give you a amount of money that's equal to the expected monetary value of the lottery, where is that going to put you in utility terms? Unfortunately, I'm not 2 meters tall, but it basically puts you up here on this utility function. Puts you up there on the utility function. Meaning that, you can see it from here, meaning that if I give you the expected monetary value for sure, your utility is higher because you're on that curved utility function. Your utility is higher than the expected utility of the lottery, which gives you this expected utility. In other words, right, if I promise you an amount of money, that's better than having a random event that pays out the same expected monetary value. And that's exactly the definition of risk aversion. So this is one way of interpreting the utility I'm asking here, what if the same expected monetary value were paid out for sure, and I can see from comparing the two utilities, it's worth more to me if I get the amount of money for sure. Okay, so I get a higher utility. Remember here, the y-axis is the utility. Let's look at it. If we play a lottery that has an expected monetary value, that's it. I know that the utility I can expect, or the utility I get, my expected utility is here. So I can read it off, that's 100 times B. So what I'm asking, if I look at this horizontally, is I'm asking what amount of money for sure is going to give me the same expected utility, right? How much do I have to give you for sure so that you get the same utility from this certain amount as from the lottery? In other words, what's your certainty equivalent? Okay, so the certainty equivalent is going to be the point at which your utility function crosses 100 times p. 100 times p is what you expect in expected terms from the lottery. So that means that immediately what you can see here, the certainty equivalent is less than the expected monetary value. I'm willing to accept a smaller amount of money if I get it for sure than to play the lottery with an expected monetary value. So here, again, we can see from the graph, the certainty equivalent being lower than the expected monetary value is a sure sign that someone is risk averse. Someone is risk averse because it's willing to take less in certain terms than something expected. So same thing if we look at a risk-loving decision maker. It's just that the curvature is different. The curvature goes the other way. Now what this means here is that if a risk-loving decision maker plays a lottery between 0 and 200, and the expected monetary value is this, he's going to compare the expected utility of the lottery, which again is 100 times p, and the utility he gets from a certain amount, from getting paid the same amount for sure. And so the interesting bit for a risk-loving decision maker is that he actually gets a lower utility, because this piece here, this point here, is actually less than 100 times p. This means that a risk-loving decision maker is actually happier if he gets to play the lottery than if he gets the same amount in certainty. And again, we can think about this in horizontal terms. So here, the expected monetary value is less than the certainty equivalent. In other words, you would have to pay a risk lover more. You would have to pay the risk lover more than the expected value of the lottery for him to be different between the lottery and a certain amount. So what we can think of also is here what this means in terms of the marginal utility of money of an extra 10 pounds, depending on your endowment. So if you have 0 money and someone gives you 10 pounds and you're risk averse, it means that your utility goes up by quite a bit. If you have 190 pounds and someone gives you an extra 10 pounds, the extra utility is fairly small. Because if you look at the slope here at the very end, it's going to be fairly flat. So an additional 10 pounds are not going to make much in terms of additional utility. If you already have a large endowment, if you have a small endowment, 10 pounds are going to make a lot of difference. For a risk-loving decision maker, he basically doesn't care if he's poor or somewhat less poor. right? So he doesn't care much if he gets 0 or 10 pounds. Okay? What he cares about is a higher probability of making the big prize. If you think of Mark Zuckerberg, for example, he dropped out of Harvard. It probably meant for him that he lost, in expected terms, he probably lost, let's say, $50,000 a year. Right? So if he loses $50,000 a year, for him that was peanuts, right? So this really didn't make much of a difference for him, okay? Because he regarded 50,000 as a small amount and 0 as a small amount. But what he was after was the small chance of really hitting the jackpot, right? Really being very lucky and being a multi-millionaire by founding some social network. Okay? And so therefore, entrepreneurs will be risk-loving in the sense that they're willing to take risks in return for a small chance for a very high outcome, for a very high payoff. So that's what marks out risk-lovers. Good. So I would say now is the time to take a break. So let's take a 15-minute break and. What restful decision-making could be doing, right? So it's not about describing what they do, but it's rational decision-makers, normative behavior. We're concerned with decisions under uncertainty, so it's really about trying to find out what they should be doing if they don't know exactly what the right outcome is. We know you know how to structure decision trees, how to use decision trees to structure decisions. You should figure out, or whenever you are faced with drawing up a decision tree, you know what alternatives are available, what the sources of uncertainty are, what the possible outcomes are, what the payoffs are, etc. We started out with the first 2 examples. In which we have we applied the expected monetary value criteria to decision making, and of course that's appropriate whenever we have risk neutral decision making. Risk neutral decision making, all they do is maximize. We figured out though that sometimes decision makers do not behave according to full profit maximization, but they use some sort of other decision rule. Which especially takes into account the amount of risk that people take to get to a certain outcome. And so in the development, we use the expected utility criteria of decision making. And the concept is basically exactly the same. Instead of using monetary values, we use utility values and look at expected utility. And the thing becomes then a little bit more challenging when we don't know what the utility function is of people. Right? So if we knew exactly what monetary values translate into utilities, then that would be easy. It would be an easy problem. But we need a way of finding out how to determine utilities. And the general rule, the general idea is that we take the highest utility and assign the value, or the highest payoff, the highest monetary payoff, and assign a value of 100. And we take the word 1, so some upper bound, and then we take the lowest value and assign a value of 0. And then what we know is that every monetary payoff in between the highest and the lowest will have to conform to a utility value somewhere between 0 and the maximum of 0 and 100. That's 1. Okay. We'll have an opportunity to do that in just a second. And then we also found out what the shape of utility functions is, and the utility function of a risk-averse decision maker is concave. Good. So now, looking at the multi-class. And so what I'll do sidetrack, but because I don't want to give out model answers, right? Model answers have one big problem. Model answers are suggestions for you to learn things by heart, right? To memorize it. You should memorize it. As I said, if you copy down the answer here and you memorize it, then you've wasted some small part of your brain has been wasted because that question is not going to come up in the final. Okay? So what you should be focusing on is really to understand how we got to that, how we got to that answer. So I'm going to give you a bit of time to have a look and maybe write down the answers that you feel are useful, but at the same time, I will not make them available as model answers because I think, as I said, model answers are not Okay, so in question 1, you are given 2 decision trees. You're asked which choices you would make. That's fine, and then you should show that a rational expected utility maximizer would not take the sure thing in the top tree and take the top gamble in the bottom tree. Okay? So what you're asked to show is that someone would not at the same time take this over these uncertain outcomes and take this over this. Okay? So that's the point. You're supposed to show that a rational utility maximizer would not do this and do this. And let's see how we do. Recall that when we go and look at the 2 decision trees, all we have are 3 values, right? We only have 3 different payoff values. We have 0, we have 27,500, and we have 24,000, right? That's all we have in here. So that means that even though we don't know the utilities of each of these, what we can do is we can basically set the lowest one equal to 0, we can set the highest one equal to 1 or 100, and we know that whatever's in between will give a utility somewhere in between. So that means that we set u of 27,500 equal to 1, u of 0 equal to 0, and u of 24,000 equal to x. Now, as I said, what it means to take the sure thing in the top tree, it means that we get a higher utility from this choice than from this choice. Okay? A higher expected utility from the certain payoff to the uncertain payoff. So what that means is that if a rational person, if a rational utility maximizer picks the sure thing in the top tree, this implies that the utility from the top part is less than the utility of the bottom part. So what this gives us is 0.1 times 0, 0.01 times 0, plus 0.66 times x, plus 0.33 times 1. That utility has to be lower than x. Okay? So 0.33 plus 0.66x must be smaller than x, or if we rearrange, that means that x has to be bigger than 33 divided by 34. Now let's see what a rational person who would take the top gamble in the bottom tree would have to have utility. So this means that if you take this over that, the expected utility of this outcome has to be bigger than the expected utility of that outcome. Now here, you get 0.33 times 1 must be bigger than 0.34 times x. So 0.33 must be bigger than 0.34 times x. Or x has to be smaller than 33 divided by 34. So if we then look at the two conditions here, you have to have a value of x bigger than 33 divided by 34 to make the first choice, so to take the short thing in the top tree. And you have to have a value of x smaller than 33 over 34 to pick the bottom gamble in the pick the top gamble in the bottom tree. So this means that the same person, right? The same person cannot have 33 over 30 x bigger than 33 over 34 and x smaller than 33 over 34, right? So this means that these choices are inconsistent with expected utility maximization. So you would not expect a rational person to make these two choices in conjunction, right? Make both of these choices, because it would imply, on the one hand, that we have a large x, and on the other hand, that we have a small x. So how to approach these questions, how to approach this particular kind of question? Well, I guess important here is that you know what to do. It's also important that you know what the question is. I think that's what many people struggle with for a bit. So a rational utility, expected utility maximizer would not take the short thing in the top tree and take the top gamble in the bottom tree. So here, it's simply saying that the same person, right? The same person would not do one and the other. And that's what you need to take into account here. And then once you see, and I guess that's also a common thread if you look for financial outcomes, if you look for monetary outcomes here, you have 3 different monetary outcomes, so it's easy to pick the smallest, giving it a value of 0, the largest, giving it a value of 1, and so therefore the one in between has to have utility in between. And so that's also a useful thing to use. Okay. Good. Now, question 5. Question where the entrepreneur has a project, gets an R with the probability P and 0 with the probability 1 minus P. To start a project, he has to get a loan of X, and the bank is going to require a payment of D if the project is successful. It will not be paid back if the project is not successful. If the entrepreneur gets a loan to start the project, and then further follows whether or not the project is successful. So think of the cost of C as basically the cost of getting out of bed and putting in effort and so on. That's more like a cost of effort. And that effort is not something you will ever get back. Okay, so it's something that you pay regardless of whether your business is successful or not. Plenty of sub-questions. The entrepreneur will start the project, and here we get, again, one of the first cases where we're seeing what I mentioned a few times already. You need to be able to set up the right objective function. Right? So you need to be able to set up what it is that you're trying to determine, what it is that you're trying to figure out. Well, you should determine the minimum P, the minimum probability for which the entrepreneur will want to start the project. Now, what does it mean you want to start the project? It means that you are better off in expected terms if you start the project than if you don't. So I will start the project if my I will want to start the project if my expected returns are bigger than 0. Now my expected returns are P, that's the probability that I'm successful, times R, that's the returns I get, minus C, these are the costs that I have to incur anyway, minus D, that's the repayment I have to give to the bank, plus 1 minus P, that's what happens if I'm unsuccessful. If I'm unsuccessful, I don't pay back, I don't get any returns, but I still have the cost of effort, that's C. Okay, so it's P times R minus C minus D. That's the case if I'm successful. And minus C is the case if I'm unsuccessful, and that's 1. So that has to be positive, and that means that I have P bigger than C divided by R minus D. So as long as P is bigger than that number, I'm going to want to start the project. Then you were asked to determine the value of P, which gives the bank 0 expected profit. And here again, you're supposed to find the profit function of the bank. Right? So what profit, what payoffs can the bank expect? And the expected profit is equal to P times D. So that's P, the success of the project. If the project is successful, you're going to get back D as the bank. So the repayment is D. And then minus X is what the bank has to pay out in any case, right? So they always pay out the loan, and in a probability P of cases, proportion P of cases, they're going to get back the repayment of D. And so if you set that equal to 0, then the bank's value of D, so the repayment of D, is going to be P equal to X divided by D. Now we're assuming that there's a population of entrepreneurs. They have these kinds of projects, but they don't have the same probability of success. They're heterogeneous in terms of probability. And here we assume that P is uniformly distributed between 0 and 1. I know my own probability of success, but the bank doesn't. We then assume some numbers. Given D, which entrepreneurs, meaning which values of P, will want to go ahead with the project? I'm almost sure that that's a much simpler answer. Now, given that there's a value of D, we can now say, well, every entrepreneur who has a probability of success that's higher than the minimum probability is going to go ahead with the project. So therefore, given that we have A, we have P has to be bigger than C divided by R minus D. We can plug in the numbers here, and we get P must be bigger than 100 divided by 500 minus C. can be asked for the average success probability of the entrepreneurs who take out the loan. Okay, so we know what the minimum success probability is, and that's basically the one that we just solved. Right? That's P must be bigger than 100 divided by 500 minus P. So what's the average success probability of the entrepreneurs to take out a loan? Well, to do that, let's take a step back. So we know a couple of things. We know that the entrepreneurs are heterogeneous in their success probability, meaning that some people will have a success probability that's very close to 0. Some people will have one that's very close to 1. We have a uniform distribution between 0 and 1, right? Now, that means that, so what this basically comes down to, what this question comes down to, is knowing what the average value of a distribution between the upper and the lower bound is. So, if you were to look for the average value of a uniform distribution between 0 and 1, what would be the average value of that? It would be 0.5, right? That's pretty good. If you were to look for the average success probability, the average probability of the distribution between 0.5 and 1, the average value of that would be 0.75. Right? Okay? We have a uniform distribution. All we do is take the lower bound and we take the upper bound and we take the midpoint between that. We take the average. So if we have a lower bound of 100 divided by 500 minus P, right? We know from question C that's the minimum probability for which an entrepreneur would want to undertake a project. Okay? That's 100 divided by 500 minus P. We know what the maximum probability of success is. That's 1, right? And so therefore, if we wanted to take the average between the minimum and the maximum, we just take 1 plus, so the minimum plus the maximum, or the maximum plus the minimum, divided by 2, right? That's the midpoint between the maximum and the minimum probability. And so we simply take 1 plus 100 by 500 minus D divided by 2. That is the average of the entrepreneurs that will undertake the project. Okay, so if I ask you for the average of a distribution between 0 and 1, you know it's 0.5. If I ask the average of a distribution between 0.5 and 1, it's going to be 0.75. If I ask for the average between 100 divided by 500 minus D and 1, it's going to be the midpoint between the two, which is minimum plus maximum divided by 2. Okay? So you're then asked to determine D such that the bank's expected profit is 0. So it's all kind of building up very clearly. The bank's expected profit is basically D, that's the repayment, times P, that's the success probability, minus X, that's the loan, right? So we know what the loan is. We're trying to find out what D is. So what's interesting now is the success probability. Now that means that if I'm the bank and someone shows up on my door and says, I want to take out a loan, my expectation of this guy's success probability is basically the average probability of those people who want to take out a loan, right? So it's going to be 1 plus 100 by 500 minus D divided by 2. And if we take that, that's basically an equality, an equation in the one unknown. If we solve for D, it's going to give us D equal to 276.4. So of course, what you'll find is that there's also a second solution, something around 726. But of course, that's not relevant given that this would be bigger than the rewards, bigger than the returns, and that's ruled out by it. So solving for D gives you D of 276.4. And then question F is really a bonus. By calculating average success probability and determining that the mixture property given the probability. Well, we know what D is. Right? D is 276.4. We know that the average success probability is 1 plus 100 by 500 minus 276.4 divided by 2. So if we solve for that, we get 1 plus 100 by 223.6 divided by 2. So we get a success probability of about 72%. And then if we just plug in 72% in the expected profit function of the bank, it's going to be 0.72 times 276.4 minus 200, and that turns out to be 0. So it's obvious that this question you can only get right if you get E and D right. But once you've got that, these are nice extra points. So when we think about this question, one thing to keep in mind is that this was a long question, which meant that we had 45 minutes to solve this. Okay. Doing the maths, doing the algebra would take you maybe 15 minutes, if I'm being conservative. So let's make it 20. Okay. Even if you take 20 minutes for the algebra, that means you've got 25 minutes to actually think about the question. And that's probably a pretty useful thing. If you start doing the algebra straight away, I would say 4 times out of 5 you're going to make some mistakes. Not mistakes in terms of the algebra, but mistakes in terms of how to set up the question. The thing that was challenging in this question was actually figuring out how to set it up correctly, right? So it was all about setting up the entrepreneur's problem, and when does he want to undertake a loan? He wants to undertake a loan if his expected profit margins are positive. What is the bank's profit function? The bank's profit function is basically the likelihood that it will be paid times the repayment minus the loan that it takes out. And then it was about finding the optimal value and the average value. So again, the main challenge here was setting up the problem. It's not doing the math, not doing the calculation. So I think that here, 25 minutes thinking is well spent. It's much better spent than 25 minutes chasing up the algebra that is probably about the wrong question anyway. Okay? So do spend time, do take time, and many long questions are like this, especially many long questions in decision analysis tend to be like this, that they don't really require a lot of super complicated algebra, but they require some thinking about what's the right way of setting up the problem, right? And do take yourself the time. So I'm gonna stress this again tomorrow afternoon, that there's no point in rushing through 180 minutes, right? You will not need the 3 hours. I'm almost certain that you won't run into tiny problems. You might more likely to run into problems of making mistakes where you don't make mistakes, right? So time is not rather take your time rather than rush through something that isn't going to do it right. Okay? So, and I think this was a prime example of it. Good. Now, as I mentioned, the second big part, the second topic I want to cover today is game theory. And situations where there is some strategic interdependence. Strategic interdependence is place or is given whenever we have decision makers, which we call players in game theory, that will take the strategic behavior into account, the strategic behavior of others into account when making their own decisions. So in other words, I'm going to form expectations about what my rivals, what the other players in the game are going to do, and I'm going to behave accordingly. Importantly, strategic interdependence also means that my behavior will affect the profits or the payoffs of others, and the behavior of others will affect my payoffs. Okay? Otherwise, we wouldn't have an interesting situation. If I can do whatever I want and you're unaffected by it, and you can do whatever I want, whatever you want, and I'm unaffected by it, we're not really in a situation of strategic interdependence, because what I do doesn't affect what you do. We're focusing on non-cooperative game theory, which means that all we care about is that each player maximizes their utility. Okay? That is something you know, but it's something that's worth thinking about again, because often we have situations in which maybe the joint outcome, the joint payoff may be higher in one solution, but we're looking for the individual profit maximizing. So to analyze a game, we need a number of things, and we need a number of factors or pieces of information. We need to know who the players are. We need to know what the rules are of the game. The rules of the game cover things like who moves when. So is there a sequence of moves? Is there simultaneous moves? What do I know when I move? So are there any informational issues? What can they do? What are the strategies that can choose or that a player can choose? What are the outcomes of the game? So for each possible set of strategies, what's the outcome? And what are the payoffs? So what are the player's preferences over the different outcomes? These are the four segments of information, the four pieces of information that we need to be able to analyze it. So we think of an example. This is an example of the so-called coordination game. We have Mrs. X and Mr. Y as the players. The rules of the game are that they cannot communicate with each other, but they know they're supposed to meet at a certain time somewhere in London. And there's two possible places. There's the Royal Albert Hall, which is in the west of London, or the Barbican, which is in the east of London. They cannot be, so one person cannot be at the same place at different places at the same time, so they have to make a choice between the Royal Albert Hall and the Barbican. Outcome is that if they meet each other, they enjoy each other's company. So they don't actually care about where they meet, they care about that they meet. And the payoffs are that they each have had the utility of 50 to the company of the other. If they do not meet, the outcome is 0. So these are the four pieces of information that we need to solve the game, to address the game. And we're not going to do it with this one, but we're going to do it with plenty of others in the next couple of minutes. Now, there are several ways of representing games. I guess the most common one is the normal form of a game. In normal form games, we assume that players use the strategy simultaneously. The normal form representation consists of players, each player set of strategies, and the payoff for each player for each possible outcome. And the form in which we know is the best is 2 players with a finite number of strategies, because then we can draw it out. And here it is by convention. Firm A is the role player, So he chooses between advertising and not advertising, so between row, the upper row and the bottom row, and from B is a column player, so he chooses between the left and the right column. This is a game in which two players play simultaneously, and they have to decide whether to advertise or not to advertise. By convention, we write the first player, the row player's payout first, and then the second player, the column player, second. So looking at this game here, we can actually use a number of things. We can use we can develop a number of concepts. First concept we're going to cover is the concept of the best response. The best response means that given the strategy of another player, what maximizes my player. So if we look at firm B, assuming that firm A advertises, this means that we're in the top row. Then firm B is going to choose if they advertise and get 6, or if they don't advertise and get 3. So that means that the best response for firm B to firm A advertising is to play advertising. The best response for firm A to firm B not advertising, that means that firm B chooses the right column, then firm A can choose to advertise and get 10, or not advertise and get 8. So firm A's best response is to also advertise. And in fact, if we look for firm A's best responses, we'll find that playing advertise is the best response for firm A, regardless of what firm B plays. Meaning that if firm B goes for the left column, so they advertise, it's going to be best for firm A to advertise as well. And if firm B doesn't advertise, it's also going to be best for firm A to advertise. So it's a best response for firm A, regardless of what firm B plays. This means that to advertise is a dominant strategy for firm A. A dominant strategy, therefore, is a strategy that's always the best response, regardless of what the other player plays. Now, of course, we can do the same thing for firm B. Now, if firm A advertises, then firm B is better off advertising as well, because they get paired 6 rather than 3. And if firm A doesn't advertise, then firm B is also better off advertising, because they get 11 instead of 7. So, to advertise is a dominant strategy for both firms, which means that the equilibrium is to advertise firm A and to advertise firm B, and the equilibrium payoff is 6-6. Again, this is not a big deal, but if we want to be precise, and if you want to avoid losing easy points, then whenever you talk about the equilibrium, you talk about the combination of strategies. Whenever you talk about the equilibrium payoff, you talk about the outcome. Right? So the equilibrium payoff is whatever is in the cell. The equilibrium itself is whatever is outside the cell. So that's advertised and advertised. Okay? Like I said, it's not a big deal if you get the right answer. You're going to get pretty much all points, but maybe not every single point. Maybe you're going to lose out 1 or 2 points. Right? If you lose 1 or 2 points and you're at 65, it doesn't matter. If you lose 1 or 2 points and you're at 39, it matters. Right? So just make sure you get these ones right. Now, we talked about an equilibrium just now. So what does it mean to be an equilibrium? What does an equilibrium mean? Nash equilibrium is a combination of strategies on certain players such that no player can possess a by unilaterally. So I told you that I've been coming here for 10 years, right? means I know the administration really well. And I got the administration to give me all your phone numbers. And I'm going to call one of you this morning at 4 a.m. And I'm going to ask you for the definition of national. And if I wake you up, which I hope I won't, so you can also hope, one of you 250, one of you 250. To give me this. Why do I have to give it? Why am I asking for this? I'm asking for this because the Nash equilibrium is such an important concept in this entire course, right? Nash equilibrium, and I mean, I know that kind of you can look at the matrix and you can find the equilibrium and you can sort of cross out and circle things and so on. That's all fine, right? But the Nash equilibrium is a much deeper concept. The Nash equilibrium is really about trying to find a resting point at the game. Okay? And I've seen many questions that are asking for an equilibrium without the matrix like this, right? So a couple of years ago, I recall that there was a question, I think with two people with first names A and B. So I don't know, Arnold and Burke. Okay, they have valuations for a house. One has a valuation of 1 million, the other one is 1.1. Then it says, well, show that it's an equilibrium for each player to fit the other player's valuation, right? And you're then asked to show what's the valuation, what's the equilibrium, that it is an equilibrium. To do that, okay? And for that, it's just fundamentally crucial to know what a Nash equilibrium is. Right? It's fundamentally of importance that you know what this is. And that's why, really, when you're being asked, or when you're trying to define what a Nash equilibrium is, really should know what it is. Okay, so let's dissect this for a bit. It's a combination of strategies. So whenever you're looking for a Nash equilibrium, we want to look for all the players playing a certain strategy, right? So here we're looking for player A and player B, choosing top bottom for player A, left right for player B. So a combination of strategies. We need one behavior for each player, such that no player can do better. Okay. So here again, it's about being able to do better, which means that you could not improve your payoff in a Nash equilibrium. Again, I often get asked, so we're gonna have one game theory question, and some of you are going to wonder why we have a weak inequality rather than a strict inequality. Okay? Now, this is related to the Nash equilibrium. The Nash equilibrium says that you cannot do better, which means that if you could change your behavior and get the same output, that still doesn't give you an incentive to move from that current output, from that current combination of strategies, right? So if you're currently driving on or if you're currently choosing left strategy, something, right? You're currently choosing the left, or the strategy 1. And if you could choose strategy 2, and that gave you the same output, that would not be an incentive to choose 1 instead of 2 or 2 instead of 1. You are equally happy with both, which means that there's no incentive to change from what you're currently doing. Okay. So that's the second point. No player can do better, meaning that we're completely happy with weak inequalities. Because if I get the same output and the same payoff, I still have no incentive to change. And then this is really the most important part. This is the most important word here. It's unilaterally deviating. What does that mean? Unilaterally deviating means that we take the other strategy as given and we see whether we can do better by doing something else. Okay? So that's the important bit. We take the other strategy as given and then we see if we, given that other behavior, if we can do anything better. Okay? So that is important. That's also a concept that shows up so often. It shows up in oligopoly theory. It shows up in bargaining. It shows up in auctions. These are all cases or these are all applications of game theory. All you're supposed to do there is really find the natural equilibrium. Right? So do keep that in mind. And that's why this is such an important concept, such an important principle that you really should know. So when you come and ask me questions later on today, I'm going to reserve the right just to ask you for the definition of a natural equilibrium. Okay? Just because I'm nasty like that. No, so don't, I mean, literally, I really think that this is an important concept. I really, really do love this. Not because I'm super excited. Well, I am super excited about the natural equilibrium, but not because I'm. It's just an important concept. Full stop. Do it for managerial economics. Know it. Full stop. Okay. So, what we can draw, we just looked at best responses. Best responses are, right? Best responses are, if you choose a certain behavior, what maximizes my profits? What behavior maximizes my profits? That's going to be a best response. So that by definition means that Nash equilibrium strategies are best responses to each other. So therefore, if I take your strategy as given, and I'm playing a best response, and you're taking my strategy as given, and you're playing a best response, we're in Nash equilibrium. By definition, this is the case. Because we're looking at a combination of strategies such that no player can do better by unilaterally deviating. Unilaterally deviating, again, means that we take the other strategy as given. If I already play a best response to your behavior, and I'm assuming that you continue doing what you do, I have no incentive to deviate, right? I have no incentive to change my behavior if I already play a best response. Meaning that in a Nash equilibrium, two best responses match. Okay? Two best responses coincide. So in the example above, we have two Nash equilibrium. We have bottom left and top right. So let's just see if that's actually the case. So if player A chooses B, he chooses bottom, and player B chooses left. If player A chooses bottom, then player B can choose between left, which gives him a payout of 8, or right, which gives him a payout of 4. So of course left is the best response. If player B chooses left, then player A can choose between bottom, which gives him 6, or top, which gives him 5. So again, bottom is the best response. So here, bottom and left is a combination of best responses. It's a Nash equilibrium. On the other hand, if we look at top right, if player A chooses top, then player B chooses between left and getting 3 and right and getting 5. So right is the best response. And if player B chooses right, then player A could choose between 10 and 2, so top and bottom, and he could choose top. So again, top right is a combination of best responses. It's an action. Good. And there are a couple of nuances about an action equilibrium. Top left in this game is the only Nash equilibrium. We can check this, but you can also take my word for it. Player B playing left means that player A wants to choose top. Player A choosing top means that player B wants to choose left. So it's a Nash equilibrium, that much we can say. It's the only Nash equilibrium, but just looking at this, at the matrix, top left is doing okay. So player A gets 2, player B gets 1. But actually both could be made better off if they switched from top left to bottom right. So instead of getting 2 and 1, everyone would get 1 more. Everyone would, so player A would get 3, player B would get 2. So in a Nash equilibrium, bilateral deviations could work, but not unilateral deviations. So bilateral deviations would mean that both player A and player B would change their behavior. If A moves from B to B and B moves from the left to the right, this would give both of them higher payoffs. But that's not what we're looking for when we're looking for an equilibrium. In an equilibrium, we're just looking for situations that cannot be improved by unilateral behavior, right? But assuming that the other player sticks to what he's doing, and I'm changing. And in fact, as I just said, this natural equilibrium on top left doesn't seem to be the best outcome for both. And in fact, it doesn't seem to be Pareto efficient. So I would hope that you still know what Pareto efficiency means. For those of you who like a quick refresher, a Pareto improvement is where you make one player better off without making the other one worse off. And in this case, actually, both would be made better off. Right? So I get 2-1. So Pareto efficient in that case means that we cannot make anyone better off without making anyone else worse. So here, we could make both better off, but that still doesn't mean that the top left is not an equilibrium. And often people confuse the natural equilibrium with something like the optimal outcome, right? The best outcome. This is not necessarily the best outcome, right? It's just an natural equilibrium. Good. So we're now going to look at a number of different, say, classical games that we see over and over again in different settings. One's called the Battle of the Sexes, or a coordination game. That's pretty much got the same structure as the one that we looked at the start, with Mrs. X and Y. Here I'm looking at bargaining over common standards. One example would be choosing the successor of the DVD. So there's two designs, two product designs. There's Toshiba and Sony. It's clear from this that Toshiba prefers the HD DVD system and Sony prefers the Blu-ray system, because if both firms choose the HD DVD system, Toshiba will get 10, and if both chose the Blu-ray system, then Sony will get 8. Okay. We have in a coordination game, in a coordination problem, we have at least two natural equilibriums, right? It's a question of what you coordinate on. So it then becomes, the interesting bit is not whether there is an equilibrium. In fact, we have too many equilibria. We don't really know which one to choose. And just think of, we can think of many other coordination games. The one I always think about is, especially when I come to Singapore, is the side of the road that people drive on. Right? So if you're in continental Europe, people drive on the right side of the road. If you're in the UK, if you're in Singapore, if you're in Japan, people drive on the left side of the road. Now, is any one of those better? Surely not, right? That doesn't make much of a difference. On the other hand, it doesn't make much sense if I, as the kind of the continental European, decided that I'm going to educate the UK in driving on the right side of the road. And so I'm just going to set an example and say, okay, I go to the UK and I drive on the right side of the road. Right? That's not going to work for very long. Right? So I'm going to be dead before I know it, because everyone else is going to drive on the other side. So it's a coordination problem in the sense that there are two natural equilibria. Either everyone drives on the right or everyone drives on the left. But there's no mixing, right? So we cannot have a mixture of behavior. How to select this is completely arbitrary. In this case, because everyone, there wouldn't even need to be a law in the UK that I have to drive on the left side of the road, right? If I come into the UK, it's in my complete best interest to also drive on the same side of the road as the rest of the people, right? So history basically solved the game. An interesting instance here was in Sweden, which was driving on the left side of the road and then eventually decided that they wanted to change to the right side of the road. And how do you do that? I mean, this is literally, there's cars out there all the time. And Sweden at some point had to decide that we're going to go from the left side of the road to the right side of the road. Right? And you can't do this gradually, right? You can't do this slowly but surely. You have to do this in one big bang. So what they did is they did studies on when there's the least traffic. They also did studies on when people are the most alert. I mean, if you were looking for the least traffic, you would probably do it at Sunday 3 a.m. or something. So on a Sunday at 3 a.m., no one's out on the road, but then the next morning people get up and they're still half sleeping, and then they don't know which side of the road they should be driving on. So what they did is they chose a Tuesday at 4 p.m. something. So Tuesday at 4 p.m. All the cars have to stop, settle down for 1 minute, and then switch sides on the road. So it's a really interesting coordination problem, because once you have an equilibrium here, once you have settled on an equilibrium, it's really hard to move from one equilibrium to the next. So yeah, kind of an interesting anecdote there. So what we don't model in a game like this is that some firms may actually have an incentive to move first. So in this case, in the coordination game, both firms actually have an interest in being the first mover. So if Toshiba were the first mover, then they would choose the HDDVD design, and it would be in Sony's best interest to also choose the HDDVD design. Okay, so these are coordination games. Now we've got it's called a chicken game. Chicken game because in American terminology, someone who's a coward is a chicken. So here, there's, for example, this might happen in negotiations where two firms are negotiating with each other. If they both negotiated in a soft manner, this would be their joint optimizing outcome. But each of the players, each of the firms has an incentive to negotiate in a tough way. So firm B chose a soft negotiation strategy, so they would be in the right column. Then firm A has an incentive to go tough, because tough gives them 100, soft gives them 70. So again, what we see here are two natural equilibria. And the two natural equilibria are that one firm plays soft and the other one plays tough, and vice versa. So this means that for both of the firms, it's actually a good thing if the other player thinks that I'm a tough negotiator. Right? So if firm B believes that firm A is going to choose a tough strategy anyway, it's best for firm B to play soft. If it thinks that firm A is going to be soft, it's better for them to play soft. Right? So here it's actually useful to convey some information, useful for to make the other firm believe that you're going to react or you're going to behave in a certain direction. So playing these kinds of games, actually building beliefs about yourself or conveying beliefs, signaling types of behavior is a useful. Okay, now the final game, and that's a game, of course, that you all know very well, and you know it in many different contexts, many different techniques, is the prisoner's dilemma. And the prisoner's dilemma Business dilemma can come in many, many shapes and forms. We look at the advertising game, that actually was a business dilemma. Many others are. Here is just in the context of team production. We've got two workers in a team that can either kind of pull their weight in a joint product or in a joint production process or not. And if they participate, we call it colluding or cooperating. If not, we call it defecting or deviating. The employer can only observe joint outputs. There's no way of proving that one person didn't work hard and the other one didn't. So this is basically how it looks like. So we've got worker A and worker B deviating or cooperating or defecting and colluding. It's clear that the best outcome would be for both to cooperate. But once the other player cooperates, it's in the best interest of the other player to deviate. Okay? So it's in fact a natural equilibrium in dominant strategy. Both firms will both workers will end up defecting. Both workers will end up getting one because it's a dominant strategy. Whatever the other player does, whatever the other worker does, is always best to deviate or to defect. Payoff is not Pareto efficient. We could make both players better off by going from DD to CC. So we would improve our payoff by 2. And there's no collusion, so there's no cooperation if we cannot enforce it in one way or another. So we just play this game a single time. We both have dominant strategies, not to cooperate.